This week's real shift is that AI is starting to control its own mistakes instead of just being steered from the outside. One line of work shows conditional generation can use feedback loops to correct misalignment on the fly, even when the constraint is non-differentiable. Another pushes video generation toward true narrative pacing, with keyframes as semantic anchors. And a third proves a fully open diffusion language model can scale to serious benchmark performance. The common thread: generation is becoming more interactive, more controllable, and less dependent on brittle prompt tricks. Let's explore the first paper, Flowbender Feedback Aware Training for Self-Correcting Conditional Flows. Flowbender, from Technion and NVIDIA with collaborators at the University of Toronto and the Vector Institute, reframes conditional diffusion and flow matching as a closed-loop control problem. Instead of treating the condition as a static queue or relying on hand-tuned inference time gradients, it trains the model to consume its own alignment error and learn a nonlinear correction policy. The method uses a two-pass sampling step, where an unguided look-ahead estimates the clean sample, the forward operator computes a feedback signal, and a refinement pass outputs the corrected velocity. It supports both first-order gradients for differentiable operators and a zero-order residual variant for black box or non-differentiable operators such as JPEG compression. Across image translation, restoration, and 3D mesh texturing, Flowbender consistently improves fidelity and plausibility simultaneously. On super resolution, it reaches 44.07 PSNR and 98.96 SSIM, with first-order feedback versus 34.35 and 96.88 for standard fine-tuning, while zero-order feedback attains 3.36 FID. On JPEG restoration, it improves from 26.29 PSNR, 79.45 SSIM, 22.24 LPIPS, and 4.35 FID to 28.86, 83.13, 16.33, NWW, DULP, and 3.8. And on Objaverse texturing, it lowers FID from 8.74 to 6.64, while raising MPSNR from 21.91 to 26.39. The paper also shows that a prior step shortcut reduces inference to as little as n+1 evaluations for n-step sampling, and an ablation finds pun equals 0.1 is the best null feedback probability, while orthogonal decomposition reveals that about 80% of the correction energy lies outside the guidance gradient, confirming the update is not just gradient steering in disguise. Let's explore the second paper, Smart Director, Keyframe, Conditioned, Cinematic Video Generation with Narrative Pacing Control. Smart Director is a two-stage cinematic video generation framework for arbitrary keyframe conditioning that targets single-shot synthesis, multi-shot narrative generation, and video extension. Built on an internal 32B diffusion backbone for Director Gen and WAN 2.25B for Director SR, it replaces direct latent keyframe insertion with a multi-chunk VAE that encodes each keyframe as the first frame of its own chunk, then applies full spatio-temporal attention in a DIT and a custom MC rope temporal scheme to avoid boundary artifacts. The second stage uses high-resolution keyframes as semantic anchors to super-resolve low-resolution outputs, recovering faces, text, and other fine details. Trained on curated cinematic footage from copyright-free movies plus ultra video for super resolution, Smart Director is evaluated on a benchmark of 250 single-shot and 250 multi-shot videos at 24 frames per second and native 1080p or higher. It sharply outperforms Dreamina multiframes, cutting FVD from 226.85 to 41.12 inches single-shot, and from 251.83 to 65.65 inches multi-shot, while raising Gemini. 3. Pro-semantic scores from 83.87 to 91.3, and from 59.32 to 88.48, with narrative coherence gains especially large. In human study, 30 participants judged 500 video pairs, and Smart Director achieved a 54.73% win rate in multi-shot overall quality. As a standalone super resolution method, it also reduces LPIPs versus Spark VSR on all four benchmarks, showing that keyframe condition generation and restoration can be unified in one narrative-aware pipeline. Related model and evaluation infrastructure comes from Google, Gemini, Qwen3, VL, and NVIDIA training on 40 GPUs for 20,000 steps. Let's explore the third paper, Sumi Open Uniform Diffusion Language Model from scratch. Sumi, from Tohoku University, is presented as the first fully open uniform diffusion language model, pre-trained from scratch at large scale. A 7B parameter bidirectional transformer trained on 1.5T tokens, with a generalized interpolating discrete diffusion objective in its SNR reparameterized form. The authors train on 288 NVIDIA H100 GPUs for 43,308 GPU hours. Using a Llama-style architecture with 36 layers, hidden size 4,096, 100,278 token vocabulary, and a fixed canvas length of 2,048 for evaluation. On 13 benchmarks, Sumi reaches 51.1 on MMLU, 32.8 on GSM-8K, 22.6 on Human Evol, and 26.6 on MBPP, outperforming the open autoregressive baselines they evaluate under the same protocol on knowledge and coding, while lagging on common sense tasks such as PIQA at 66.4, HelloSwag at 60, and Wino Grand at 60. The paper also reports exploratory generation behavior. Confidence-based sampling induces a visible commit order. Coding tasks retain near baseline accuracy up to 4 tokens per denoising step, and extra revision passes change at most 1% of final tokens without improving accuracy, suggesting that uniform diffusion offers flexible generation but not automatic self-correction in this setup. That's a wrap on today's AI paper highlights. Thanks for watching.